Hello everybody. Today we're gonna talk about the selfish gene, the second chapter, the replicator. And last episode was about the first chapter, and now today is the second chapter, the replicator. And this one is about before life began, kinda, where it first started. And evolution is, well, Darwin said, it is the survival of the fittest. Survival of the fittest is a tiny special case of the more general rule of survival of the stable. So what that means is, what's stable stays. What is not stable breaks down. So it's simple. Like, stuff in this universe tends to be more stable. So like a bubble, a soap bubble. Soap bubbles look round. They look spherical. The reason is, being spherical is the more stable form of being a bubble with air trapped in it. If it looked like a cube, that shape would break down and form a sphere, which is more stable. Stuff tend to be more stable, not unstable. Unstable stuff get to be stable after a few after time passes a little bit. And also stuff like salt crystals form a cube pattern, and in that way grows. And salt crystals they look like cubes because being a cube is the most stable for salt crystals. And there are much more stuff that are like this. Like, let's say you make a tower out of little pebbles and it falls over. Why did it fall over? Because it was unstable, and it fell over and became stable. And the universe works like that. And you can also think about being stuff into being stable. You can think about the hemoglobin molecule. This is a protein molecule that is in our blood, and hemoglobins they are made out of amino acids because it is a protein, and proteins are made out of amino acids. And a hemoglobin is made out of 574 amino acids, and these 574 amino acid molecules, they form a hemoglobin molecule by kind of attaching themselves and being tangled up and kind of forming themselves into a three-dimensional shape. And if you look at the model of the hemoglobin, and if you do that, you'll think that it looks kind of like a thorn bush, a very tangly, complicated shape of a thorn bush. But there is something different to a thorn bush, the shape of a thorn bush and a hemoglobin molecule. Thorn bushes, if you have 10 separate thorn bushes, they will all look kind of different. They might look similar if they are all the same species. They would look similar, but if you observe them more closely, there might be this twig looks a little bit different from that bush, and this this part is more curved than that one, and so on. It would look quite different from each other. But if you look at hemoglobins, you have 10 hemoglobin molecules. They are all the exact same. Nothing is twisted or out of place. They are just, there is one hemoglobin shape, and all hemoglobins are this shape, because this shape is the most stable. Hemoglobins tend to be this shape because it is the most stable. And for this reason, hemoglobin is a molecule used to teach that stuff tend to be stable. And like you can see from the hemoglobin molecule, atoms just, if you have atoms, a group of atoms, and you give them some energy to the atoms, and then the atoms will fall into a stable form, and the atoms will just stay that way. And something like this, everything just falling into a stable form and staying like that, and the unstable ones getting rejected from the environment and turning into stable forms. This was the first, most basic form of natural selection. But how did us and other complicated life forms come out into existence? If you have the right number of atoms and put it into some sort of container and give them energy by shaking them, it's not like you shake them for a little bit and oh look, it's the first human. It's the first human. It's not like that. Even if you, it's basically impossible shaking that to make something like some sort of animal or plant or anything like that coming out of that shaker with the atoms in it. It basically won't happen. The probability is so low, and it will take so long. And so now we can question, how did all this life stuff happen? There is a good explanation about this. This is one that Selfish Gene talks about it, but in the Selfish Gene endnote part, there is a part where it says, this is only one theory about how this all came into place, but there are more theories about this. But this, the book is saying, this is not the only one theory, only possible theory. There are much more theories about how life came into place. And so this is just one of them, and I'm going to start explaining them. Now, in about 40 billion years ago, I mean not 40 billion, about 4 billion years ago, the universe hasn't even been around for 40 billion years ago. And about 4 billion years ago on Earth, in the sea, there were a lot of molecules about, and well, some simple molecules, and like water, carbon dioxide, methane, and ammonia. Those simple molecules, there were quite a lot of them, and they would mix around. And also the weather there would have been some thundery thingies, thundery weathers, and the sun was shining. There was no ozone back then, I think, so there would have been a lot of high energy sunlight, some very strong ultraviolet lights around, and Scientists have done an experiment with the water, ammonia, carbon dioxide, and methane. They put a lot of simple molecules like those into a container or a beaker or whatever they put that in, and shine them with ultraviolet light for energy, and used electricity to make make thundery weather to simulate the old past. And they left them for a little bit, and these experiments happened a lot, and every time after a few weeks or something, they would find a weak brown soup thingy, and these were it is quite possible that these were abundant in the old past on Earth, because there were simple molecules, thundery weather, ultraviolet lights, and they mixed around to make these stuff. And we call this soup the primeval soup, and there are, well, a lot of molecules in it mixed around, and in the primeval soup things kept, well, there are a lot of energy going into them, and so in those primeval soups, molecules would have been forming and being destroyed and forming again, and that would have repeated for a lot, and new stuff would have been getting created a lot. And well, so a lot of time passes, and a thing appears, and this is called the we're gonna call this the replicator. And what a replicator is that it can make a copy of itself. It is a molecule that can make a copy of itself, and so basically it can make a copy of itself, and an exact copy. And so this single molecule, now there are gonna be more of them, and these molecules that have been produced are gonna produce more of them, and these molecules, the number of these molecules would have skyrocketed. And when you think of a replicator molecule, it's kind of hard to get the grasp of it. How does a molecule produce itself? But it is kind of simple. Let's just think about replicators as a simple mold. Think of the replicator as a template or a mold, and think of it as a chain of other molecules, other smaller molecules. And this template of a molecule, before that, the simpler part of the molecule that is a template or a mold, has an affinity to a particle. It has an affinity to the same molecule as it. So, and the other molecules all do the same. So on this molecule, the same molecule sticks onto it, and on this molecule, the same molecule sticks onto it. And so on this molecule of a mold or a template, these other molecules keep sticking onto them, and now they stick onto the original molecule, and then now they're gonna be stuck onto that molecule and form the same exact molecule as the original one. Now this falls off and does the same thing. The building blocks, the building block material, the building block molecules are gonna get stuck onto the thingies and then form the exact same thing, and they go off their journey to do the same thing. And so these sort of replicator molecules, these sort of replicators would have reproduced themselves and then they would have become very abundant in the primeval soup. And there is two sorts of replicators can be think of. So firstly, there's the thing I just spoke of, the thing that has an affinity for its own kind, and there is also another kind of replicator, a molecule having affinity for its exact opposite kind. So now that opposite one would have affinity for its opposite one, which would have been the original. So now the original molecule makes a copy of itself made out of the opposite molecules, and the opposite molecule would make the original molecule. So it still goes on and produces itself again and again. And so yeah, that's how it works. And for us, life on Earth today are the second one I talked about, the positive-negative replicator. We are made out of the positive-negative replicator, not the positive-positive. But now, molecules like this, it would have taken some time for these molecules like this to form, but it would have only had to form once. So it was kind of easy, or kind of highly probable for a molecule like this to form up and rule the primeval soup world. But while making the replicas, they will make mistakes. So like on a molecule that it has affinity for, but isn't the molecule wants, maybe sticks onto it and forms a different molecule. Something like that might happen. So there would have been slightly different replicators ruling the primeval soup world, and they take resources of these replicators too. So they kind of compete for each other, even though they did not feel anything about competing. They didn't know they were competing. Just the chemistry and physics made them compete. They don't have a feeling for anything. Also, for these replicator molecules, now what is good for them? Well, firstly, longevity. Longevity is how long they live, or how long they exist before breaking down into smaller things. This is a very important factor, because the longer they live, the more they reproduce, and the more they produce themselves, the more there is this molecule in the world. So that is the first factor. And the second is fecundity. And fecundity is basically how fast you produce yourself, how fast the thing produces itself. So there are molecule A and molecule B. Molecule A molecule A reproduces about once every 1 week, and while molecule B produces itself once every 1 hour. Some time pass. Some time pass, and what molecule are there? What molecule are more abundant? Of course, it's the molecule B. Even if molecule A lives for a longer time, molecule B has higher fecundity, so it produces itself more faster. So therefore, molecule B has to be the winner in this situation. There are gonna be more. There are gonna be more of molecule B's, or more of the molecules that have higher fecundity, and so I mean also there. Thirdly, there is copying fidelity, and copying fidelity is how accurately you reproduce. So how accurately you produce the molecule that you are. So now there are molecule X and molecule Y, and molecule X makes a mistake every molecule X makes a mistake every 10 copies, and molecule Y makes a mistake every 100 copies. Now they're gonna have the same longevity and the same fecundity, but a lot of time pass, and then now what molecule is gonna be more abundant? If you count the number of the exact copies, there are gonna be more molecule Y's, because, well, it's obvious, because if molecule X makes a mistake every 10 copies and molecule Y makes a mistake every 100 copies, let's say they both make 100 copies each, then molecule X would have made 10 mistakes, so there would be 90 molecule X's in that primeval soup, while molecule Y made only 1 mistake through while making 100 molecules, while copying itself 100 times. It only made a mistake once. So if you count it, molecule X, there are 90 of them, while molecule Y, there are 99 molecule Y's. So there are more molecule Y's. So there would have been an evolutionary trend to higher longevity, higher fecundity, and higher copying fidelity. But if you know a little bit about evolution, you're gonna be a little bit confused, like, hold up, evolution happens because of evolution is a good thing, and evolution happens because of copying errors. Isn't copying errors a good thing? But if you think about it, nothing really wants to evolve. Even though we evolved from past species, and so we might think evolution is a good thing, but nothing really wants to evolve. If molecule X makes a mistake and produces another molecule, that molecule is no longer molecule X. So when the new molecule copies itself, it would copy itself, not molecule X. So does this new molecule help molecule X? No. Molecule X just used resources to copy not itself, but produce a completely different molecule. Does molecule X want that? No, because it won't help molecule X. Even though molecules don't have feelings at all, if molecules like molecule Y produce they copy themselves more accurately, that will result in more of those molecules, and so the copying fidelity, molecules with higher copying fidelity would rule the world. And that's why nothing really wants to evolve, and evolution just really happens. And also, as I said before, these molecules are in competition without knowing that they are in competition. So what that means is, firstly, the world is finite. Earth's size is finite. There's an infinite number of molecules can't be existing on Earth, because Earth's where you can live on Earth is finite, and the primeval soup isn't gonna have infinite numbers of resources as well. So there's not infinite numbers of resources, so therefore there can't be infinite numbers of so basically molecules can't be copying itself on and on and on, and for an infinite time it copies itself. That's not gonna happen because there's not enough resources. So without them knowing, they are going into a competition for resources, and so for them to get more resources, they have to either produce a lot of themselves, so more of them can copy themselves, or they can reduce the stability of competing molecules and break them and use that resources and something like that. So molecules that somehow learned to attack other molecules would have been molecules that somehow learned to attack other molecules and break them down and use those resources to make themselves. These molecules, if they appeared, there would have been these molecules would have been very abundant after they appeared in the world. There was gonna be a lot of these molecules, because breaking competing molecule stability down, breaking them down and using the resources to build themselves, not only produces itself more, it can get rid of competitors. So this was a very effective thing to do. So now some molecules that somehow learn to protect themselves, maybe by attacking the attacker, or by just simply building a physical barrier of proteins, building a wall of proteins. Molecules that learn to do those would have been very good at competing also, because it wouldn't have gotten attacked while it can still copy itself and stuff. So a lot of time passed, and some molecules attack, some molecules defend, and maybe some defenders attack too, and time passed on like that, and then there's a molecule that can copy itself with a simple protective protein wall, and while having maybe some attacking abilities and stuff. We call that a cell. Like that, the first cell appeared, and now that, as time passes on, makes a few mistakes and evolves into some better, some worse. The worst thingies get out of competition, and better thingies get to live on again, and stuff happens like that. And now that became us and the other species of life. And yeah, and the really important thing is the molecules didn't know they were in competition, but still were competing. They don't have any feelings about competing. They don't know that they're competing. When they attack, they don't have a bad feeling for the other molecule. It is just that the molecule that somehow just attack because of some chemical reactions inside their molecular body. A chemical reaction or something made it attack. It doesn't want to attack, it just does. And because it did, it just does survive. It doesn't want to survive. Things just happen, and because it just happened, we came into place. And I think that's mostly all for the second chapter. Now the molecules, they go by the name of genes, and they live inside us, the survival machines. As I said in the first chapter, or the first video of this series, I said that we and other species of life, other species are survival machines of genes. So I said genes are controlling us, but that is kind of misleading. We're not like, there's not genes inside our brain and like using the kind of stick thingies to control us. Punch that thingy. It's not like that. It's not a game or anything. Genes just build us. Proteins get built according to genes. So genes build us and kind of program us, if that makes more sense. And I think that's all for the second chapter, and I'll meet you again on the video on the third chapter, Immortal Coils. And bye.